Now, I will be performing the Young's double slit interference experiment. Let's go. So these are the materials that I used in my experiment. So the flashlight, since I don't have a laser, so I used flashlight instead, because it is the one which is available in our house. And the two slits, or the double slits, so as you can see, yes, it's double. So, and yes, and here's the flashlight. The arrangement, yes, as you can see, the flashlight and the double slits. So that is the arrangement. And as you can see, I used our wall. The wall is color pink instead of using a black paper, because when I tried the black paper, the light is not so clear. So instead, I use our wall because the light that strikes to the double slits is clear. I now turn off the light, and so I open the flashlight. So as you can see, that's the flashlight there. So if you look closely, you can probably see the double slits in this white paper. So what happens when the light passes through these two slits? So is that it spreads out. So when light passes through a narrow gap, so okay, yes, as you can see, oh my god, yes, it spreads out, it diffracts, and then the light coming from each of those two slits can interfere, as you can see over there in our wall. So here we go. So as you can see, so that as the flashlight passing through both of those slits, it's spreading out, it's diffracting, but when it gets over here, you get this very interesting pattern of bright and dark fringes, those bright, then dark, and so on. So this is a two-slit interference pattern of light, as you can see. From this, it was shown that the beam of electrons exhibits diffraction and interference patterns just like light does. This demonstrates the wave-like properties of electrons and by extension matter in general. Later, low-intensity experiments showed that even an individual electron, when passing through slits, will interfere with itself, making the wave-like nature of the electron undeniable. So it was shown that electrons act as both particles and waves, but not just electrons. Neutrons were also shown to exhibit diffraction patterns. It must be understood that since all particles are also waves, literally any object could hypothetically exhibit a diffraction pattern, so long as the object passes through an aperture roughly the size of the object's wavelength. So the question is, why does the experiment shows the wave nature of light? This is because the wave nature of light causes the light wave passing through the two slits to interfere, producing the bright and dark bands on the screen, a result that would not be expected if light consisted of classical particles. Thank you.